So, I begin with a important new topic today. This is the concept of the realization of a group, and at the next stage, as a special case, the concept of a representation of a group. When do we say that we have a realization of a group G? What is the framework needed to arrive at this realization idea? What you need is a set which I denote by capital X, and then for each element of the group you need a mapping of the set onto itself, which must have certain properties. And what are the properties? First of all, for each group element, this must be 1 to 1 and on to. So, it follows that it must be invertible. Second, you can write this in various ways. The phi corresponding to the identity element of the group must be the trivial mapping of X onto itself. Then let me not stoop too much. The third condition is that if you take two elements G and G prime in the group and compose the corresponding maps, it must be the map of the product element. This means it must preserve group multiplication, and if you put all of this together, you get also the result that the map corresponding to G inverse will be inverse of phi G. So, whenever you are able to choose a set X and on X define a family of mappings phi with all these properties, then you say you have realized the group G by a family of mappings on X. I would like you to appreciate for composition of mappings, the associativity property is always true. It is always there. But in the case of a group, we make associativity one of the requirements placed on group composition. So, we have to state it explicitly. For mappings on a set, it is always true. Now, in classical Hamiltonian mechanics, groups usually act as canonical transformations on phase space. Let me just mention it. In classical Hamiltonian mechanics, groups act as canonical transformations on phase space. And so, we speak in that context of canonical realizations of a group. In quantum mechanics, on the other hand, instead of phase space, we have the space of pure states of a quantum system, which is, as you know, always a Hilbert space over complex numbers, and you have the superposition principle operating, and therefore, because the superposition principle has to be respected and preserved, what happens is that instead of the general idea of a realization of a group on a set, we have something more specific. We are led to the concept of linear representations of groups. And it is because in quantum mechanics superposition principle is so basic, and states, pure states, are represented by vectors in a Hilbert space, we are led to the study of linear representations of groups. And this is also the reason why the study of group theory is, in a fundamental sense, very much more significant in the quantum mechanical case than in classical physics. I do not mean to say it is not important in classical physics. It is important there too, but in quantum mechanics it acquires much more structure and overall much more importance. So from now on, we will study group representations, which means linear representations. So what is a group representation? I will write the definition here. When do we say we have a group representation? What are the ingredients? Well, you must have a group in your mind or in your hands, and you must have a real or complex linear vector space, which I will denote generically by script V. We say that we have a representation capital D of the group G on V if various conditions are satisfied, which is the replacement for what I have written here. What are the conditions? First, for each element of the group, we must have D of G, which should be a linear, non-singular or invertible operator on the vector space. That's the first condition. Second, the composition law. For any pair of group elements, it must be true that sequential application of these linear operators coincides with multiplication of group elements. 3, for the unit element, identity element in the group, the corresponding D must be the unit operator on the vector space. And as a consequence of all these things, it will be true that the D for the inverse of an element is the inverse of D of G. So this is the definition of a linear representation of a group. So you see what are the ingredients. Here X was any set, phi was any set of mappings. So a representation is a particular case of realization when the set X is taken to be a linear vector space and the maps phi are linear transformations, linear maps. So everything has to respect the superposition principle. That is why we put all these conditions. These linear operators are also called linear transformations, as you have learnt probably in courses in quantum mechanics. We say that the dimension of the representation D is the same as the dimension of the vector space. So I hope I am not going too high, maybe I should not take risk. Dimension of a representation is by definition the dimension of the vector space on which you are considering a representation. So this dimension may be finite or may be infinite. We will see both in our later examples. So given a group G, in general, it can have many representations on various vector spaces of various dimensions. Okay. So a great deal, in fact essentially all that we are going to study from here on will be representation theory. Of course, at some stage we will talk about the structure of continuous groups, and then that will set the stage for their representation theory. So now a few general concepts, important concepts about representations. we have a concept of two representations of the same group being equivalent under certain circumstances to one another. Suppose I have a representation D on the vector on a vector space V and another representation on another vector space V prime. We will always assume both V and V prime are real or both of them are complex. Here is a special case which might occur, that on the same vector space we have two representations which to begin with look different. When do we say that these two representations are equivalent? We say that they are equivalent, so D on V, D prime on V prime are equivalent if and only if there is a linear invertible mapping or operator or transformation capital S which goes in this direction, let us say from V to V prime, such that the following equation holds: D prime of G is equal to S D of G S inverse for all group elements. You must check the sequence of factors on the right hand side. S is a mapping which takes vectors in V into vectors in V prime. So, in which direction does S inverse operate? V prime to V. So, look at the left hand side of this equation. D prime by definition is to be applied to vectors in V prime. D on the other hand is to be applied to vectors in V, and you can check that the two sides are consistent. What can the right hand side be applied to? V prime. S inverse will bring you back to V, D will take V to V, and then the final S will bring you back to V prime. So, this equation is perfectly sensible. Now, if there is no such S, then the two representations are said to be inequivalent. So, in most situations we are interested in representations, as we say, up to equivalence. That is, if two representations, suppose you construct one and I construct one, and then we compare notes and superficially they look different, but then we both go to Simon and ask him, please tell us, have we done the same thing or have we done something different? And he produces an S, then we say, oh, it only looks different, we have equivalent representations. So, that is why we say we are interested in representations up to equivalence. So, if two representations are inequivalent, then we say, yeah, they are really different from each other. A trivial way in which things can be inequivalent is if the dimensions of V prime and V are not the same, then obviously they cannot be equivalent.
So, this S has to be found out from that V to V prime mapping.
Beg your pardon?
S,
Matrix
S.
This
has to be found out the way we are mapping V to V.
It has, if you see, who poses the problem, who searches for the answer. I give you two representations and I ask you, find out are they equivalent or not. Then it is your problem. I have given you the problem, I am senior to you. So, if you want to answer the question, you will have to do a lot of hard work. You must try to see, is there some transformation S from V to V prime? Are you able to construct an S from V to V prime such that it has an inverse and such that it obeys this. If you are able to find it, answer is solved, you have shown their equivalence. If you are unable to find such an S, but somebody else is able to, so you have not solved the problem, but he has. The problem is to see, is there an S of this kind which obeys all these conditions? If there is, they are equivalent. If it can be shown that there is no such S, then you have shown that they are not equivalent. Okay, so that is, it's not a simple thing, it involves work. Next is a concept of representations with some additional property. We are imagining that V is a complex or it may be a real vector space. Suppose it carries an inner product which in the complex case is called a Hermitian inner product, and in the real case it is called a symmetric inner product. So the two names, and I am assuming you know these ideas, vector space with an inner product, and we will write this inner product sometimes in the usual bracket form or sometimes in the Dirac notation. So a given representation on a vector space V carrying an inner product is said to be unitary, or it's said to be orthogonal depending on the complex or real case if the following condition is satisfied. The scalar product between two vectors is unchanged by action by the group. So this must be true for all G, all X and all Y, all choices of vectors X and Y and group elements. All right. So I repeat, if V is a real vector space and it carries a symmetric scalar product, a representation on that vector space is said to be a real orthogonal representation if it obeys this condition. Scalar products are unchanged by group transformation. If V is a complex Hilbert space with a Hermitian scalar product, which means scalar product between X and Y can be a complex number, and if you interchange X and Y, the scalar product goes into its conjugate and so on such a vector space, a representation given to you is a unitary representation if it preserves complex scalar products. For the most part, we will have in mind unitary representations of groups. So it means that we are always considering a vector space over complex numbers for general purposes with a scalar product defined on it. Now, the following sometimes happens. A representation D of a group G on a vector space V is given. And let us assume V is a complex vector space for definiteness. Then you may ask, is it possible to set up a scalar product on V, a Hermitian scalar product on V, with respect to which the representation is unitary, or which is preserved by the group action? It can happen that the representation D is such that there is no way to choose the scalar product on V obeying this condition. It can happen. Here what is given to you is the vector space as a linear vector space and a set of transformations on V. The thing that you are trying to look for is a definition of scalar products among vectors with respect to which D will then be unitary. And it can happen, there is no such possibility. Oh, incidentally, I should have written number for this equation 29. So if there is no way of defining a scalar product consistent with obeying this condition, then we would say if there is no way of setting up a scalar product invariant under D, then we give D a special name. D is essentially what? What shall I call it? You're not able to obey the condition to non-unitary. So this can also happen. So it is a fact that for all finite groups as well as all continuous groups which are compact, for all these cases every representation is essentially unitary, even if it doesn't look unitary to begin with. By a suitable change, by a suitable equivalence transformation, it can be made explicitly unitary. There are, however, important cases where we have to deal with groups which have representations which are essentially non-unitary. That also happens in physical situations. Which is the group, most important group in a physical context, which has non-unitary, essentially non-unitary representations? Many of you should know Lorentz group. So one of the last section of this set of lectures, I hope to describe all the non-unitary representations of the Lorentz group, because you meet them all the time. 4 vectors, antisymmetric tensors, symmetric tensors, Dirac spinor, all of these are representations of the Lorentz group which are non-unitary. What is the reason for using the word essentially non-unitary? The idea is, you may wonder, it doesn't look unitary, but maybe I can change the definition of the scalar product on V so that the representation becomes unitary. Essentially non-unitary means it is impossible to achieve that goal. All right? Okay. So this is an example, a situation which is important in that case, and we will come to it somewhat later. Next idea, the matrices of a representation. So as always, the group is given, D representation is given on a vector space. This much is given. Well, of course, all of you know why the symbol D is used for representation. You all know?
First letter for matrix in German.
Not for matrix, but for representation in German. The word in German, I believe, I don't know the language, is Darstellung. So much of the early work on group representations was done by German mathematicians. The most famous names, so this is for group representation theory, Frobenius and Schur. So much of their work was done a little over 100 years ago, early part of the 20th century, maybe late 19th century and so on. And not very long ago, I read an account of the life of Schur. His name will come very soon, I hope, in today's lecture, Isaiah Schur. Isaiah Schur. So he was a German mathematician in Berlin. And we imagine, since this work, famous work was done about 100 years ago, they are very far away from us in the historical sense. But no, in the Nazi period, being a Jew, he was victimized and he had to escape from Germany, and he had difficulty finding a place in the world where he could continue his work, and ultimately he settled in Israel and died maybe in the 50s or some such thing. So today at lunch somebody said, I was there near me, referring to something which somebody who was around in 1955, 56, oh, that is ancient. So I got a little bit of a tremor in the heart. So for me, sure is not ancient. Valentine Bargmann, from whom I learned most of my group theory, I attended his course in ancient times. I think he probably learned from, he was around, must have had contact with people like Schur. Okay, so what are the matrices of a representation? What you do, so much of what we are studying in this section is due to Frobenius and Schur. You choose some basis, which I will denote as a collection of basis vectors E1, E2 up to En, where n is the dimension of the representation space. Then you take any group element, take the operator which represents it, apply it to one of the basis vectors. This is a vector in V, so it can be expanded in this same basis. And we will denote the expansion in this way, where there is an index k which has to be summed over, and these coefficients will be written as d superscript k subscript j, functions of the group element, and these will be complex numbers in general. If it's a complex vector space, it will be a real number if it is a real vector space. So these can be thought of as n by n matrices. And so the notation is that the superscript is a row index and the subscript is a column index. So you can see that given a representation and you choose a basis in any way you like, the representation gives rise to a family of matrices. And these matrices reflect all the properties of group representation in what you might say is explicit matrix form. So let me write out the relevant equations. You have to keep track which is a row index, which is a column index, and sum over repeated indices. The unit element in the group is represented by the unit matrix, and as for inverses, the elements of the matrix representing inverse of a group element inverse to the matrix representing G itself. So matrix inversion mirrors taking the inverse of the group element. So you have to appreciate that a group representation is defined in a basis independent way using the idea of linear transformations on a vector space, which is a concept which does not require a basis to set it up. But once you take a representation, choose a basis, in that basis this representation appears as a group of matrices. Now what happens if you change the basis? You will not say that you are changing the representation, you will say you are only changing the description of the representation. It is like taking a vector in 3 dimensions and making a rotation of the coordinate system. Then you say the vector is the same, but the components have changed. It's a similar principle here. Suppose you go from one basis to a primed basis, and let me, for convenience, write the relationship between the two basis vectors in this way. Every new basis vector is some linear combination of the old basis vectors by some set of coefficients, and that will be a matrix which must be non-singular because you're going from one basis to another. So E can also be expanded in terms of E prime, and then what you will use are SJKs. Then you can easily check the matrix D prime of G representing the linear transformation D of G in the new basis will be a similarity transformation applied to the original matrices. I am using a kind of simplified notation here. I am using the symbol D of G, depending on context, to sometimes stand for the linear transformation, sometimes for the matrix in a certain basis. So in this equation, showing what happens when you change your basis, I have written the word matrix on both sides explicitly. All right. So you can see a change of basis amounts to going to an equivalent representation. And now it is obvious that if the representation with was, let us say, unit, and if you chose an orthonormal basis for the vector space, then what can you say about the matrices? They will be unitary matrices. Detach these things in your mind. You might have a unitary representation. For some purpose, you may use a non-orthonormal basis. In that case, the matrices will not be numerically unitary, but they will be equivalent to a unitary set of matrices. Okay? So one reason for doing this in this pedantic way is to say, try not to think of a representation of a group as being given by a family of matrices. Let that come a little bit later. Let the concept of a group representation come first in your mind in a basis independent way, and think of the matrices as one of many descriptions of a given representation. Actually, this is the difference in spirit between Weil and Wigner. Weil will always define representation for you on its own in an intrinsic way, and then later show you how it can be expressed in terms of matrices. Wigner, if I remember correctly, would start from the matrix point of view. Incidentally, Wigner has written somewhere, said somewhere, Weil's book was very difficult for all physicists to read. Okay. All right. Now, some important operations with group representations. This is just a digression, if you like. For the moment, for this purpose, let us take a lowbrow approach and think of a representation of a group as being given by a family of matrices. Let us not ask to begin with whether it is unitary or non-unitary and so on. So there are three very interesting operations which produce new representations from a given representation. So what am I imagining? I am given a set of matrices representing a group of some dimension. Then we say, from this representation, we can get another representation which is said to be contra-gradient. It's not gradient, it is gradient from this representation we get another matrix representation in which the group element G is represented by the transpose of D of G inverse. So, you must do this as an exercise. If D of G is a matrix representation of the group G, so is the right hand side. That also is a representation, and that representation is said to be contra-gradient to the original representation. Then there is another procedure adjoint to the original representation, where you take dagger instead of the transpose. And the third is a complex conjugation. Take the original matrices and just complex conjugate them. So, in all three cases you must verify for yourself that you do get a representation. So, these are general definitions, and they make sense whether the representation is unitary or not unitary. Always these things make sense. Of course, we can assume we are in finite dimensions. Whenever you use this phrase infinite, it can be misunderstood for infinite. So, you have to be careful. Suppose the let me introduce a small notation which we will use all the time. A representation which is unitary is often called a UR, unitary representation. Now, suppose the representation which you started from is unitary. What does it mean? D dagger D is 1. Then what are the statements that you can make? Not all of these things are independent. If D is unitary, the adjoint representation is the same as the original. The contra-gradient is the same as the conjugate. You will see some of these things coincide. If it is real orthogonal, it is said to be self-contra-gradient, and so on. So, these are special cases in case D was either unitary or real orthogonal. But for the Lorentz group, for example, where we have finite dimensional non-unitary representations, we must keep track of differences among these procedures. Operations with group representations, which are very natural. The concept of the direct sum of two representations. So, the group is the same, capital G. You are given D1 on a vector space V1, D2 on a vector space V2. And we will assume both V1 and V2 are complex or both are real. So, they must be of the same nature. Then you first form the direct sum of V1 and V2, call it V. And I assume you know from linear algebra, you know what is the meaning of the direct sum of two vector spaces. Then we say on this direct sum, we can define the direct sum representation, which is written in this way: D1 direct sum D2. How is it defined?
I have a comment.
Yes.
You will be very kind to many people who will just spend 1 minute to explain what is direct sum.
What is direct sum? Okay. One way to define direct sum is to say, take
If your base is dependent definition,
a what?
even if you choose a basis that you know itself.
I would like to try and avoid that. Let me put it this way: V1 and V2 are two vector spaces. Both are real or both are complex. invent expressions of this kind where x1 is a vector in V1 and x2 is a vector on V2. The plus sign is to begin with not defined at all. You can't take a vector from one vector space and add it to a vector in another vector space, but invent such expressions, and on these expressions define the operations of multiplication by complex numbers, addition of such expressions. So take one expression of this kind, another expression of this kind, and declare that the result of adding them is this expression. And now what you need to appreciate is that the plus sign is appearing in three different senses. Here it is a formal symbol, something which we are setting up and defining. Here also it is a formal symbol. Here it is a formal symbol. Here it is not formal. It is the addition operation of vectors within V1. Here it is addition within V2, but we use the same plus sign. Here it is a formal new symbol. This is how we will define the adding of two expressions of this kind. And then we will say if lambda is a complex scalar, multiplication of this object x1 plus x2 shall mean multiply x1 by lambda, multiply x2 by lambda, and then formally add them. Now you can see here why V1 and V2 must both be real or must both be complex, because it must be meaningful to apply the same scalars in both for both vector spaces. So this is a basis independent way of defining the direct sum of two vector spaces, and you, if it is new to you, you must convince yourself this is a well defined, a bona fide vector space, linear vector space. Complex if V1 and V2 are complex, real otherwise. I think I will not introduce basis. So now you are given, and so this V is called V1 direct sum V2. Now on this direct sum, a representation of the group can be defined, and we proceed in the following way. Take a vector x in the direct sum vector space. By definition, it is the formal addition of something in V1 and something in V2. Write it as x equal to x1 plus x2. Then here is our definition of the direct sum representation. We do the natural thing, apply d1 to x1, apply d2 to x2. The first term is a new vector in V1, the second is a new vector in V2, add them formally. So you can see that this capital D built up out of d1 and d2 is also a group representation, and it is said to be the direct sum of the representations d1 and d2. Now going back here, you can see that the dimension of V is a dimension of V1 plus the dimension of V2. So when you take two group representations of some dimension each and then you construct their direct sum, the dimensionalities again will add up. The new representation which you have constructed has a dimension equal to dimension d1 plus dimension d2. Okay, so it's quite trivial. So this is one operation which is very important and which is very basic for group representation theory, because later on we will see we will be doing the inverse operation again and again. Yes?
What are the benefits of defining this way in basis independent way?
That is the advantage, basis independent. Conceptually it tells you to understand this concept you don't need a basis, that's all. Suppose I had defined it introducing a basis in V1 and a basis in V2. Then after giving the definition, I must do some more work to convince you what I have done is actually independent of the basis. Suppose I didn't do that. You will go home with the impression I have defined something which depends on what basis I choose here and what basis I choose there. So that is not fair to you. I should not let you go with that impression. So if I start from the beginning with a basis dependent definition, apparently basis dependent definition, I must follow it up with a demonstration. Actually, there is no dependence on the basis. This is much cleaner. I never introduce the word basis anywhere. So it is clear from the start that it is a intrinsic operation. Okay, that is why it is important. So when possible, try to understand things in a basis. Or after all, what's the difference between the way Maxwell wrote his equations and the way Gibbs and Oliver Heaviside learned to use three-dimensional vectors? There is a difference, isn't it? Once you learn how to use cross product, dot product, curl and divergence directly in vector notation, you can write Maxwell's equations in 2 lines. Poor Maxwell had to write 10 lines or something. Can you imagine? One can't see the relationships between equations easily. So the basis independent approach, initially you might say, you may feel reluctant. It involves a little bit of mental effort, but it is well worth it. Even in quantum mechanics, you are familiar with it. You have Heisenberg's matrices, you have Schrodinger's wave functions, and it's only with Dirac notation you realize those are 2 ways of representing something which should be and can be understood in a basis independent way. It makes things a little abstract, but it is very beneficial in the long term. Okay. The companion, the next operation with group representations is the formation of the direct product of 2 representations. Given D1 and D2, we define a representation D written as D1 with a cross and a circle around it in D2, which is called the product of the representations D1 and D2. And it is clear how we must do it. We start with the vector spaces V1 and V2 and consider what? Their tensor product. Now, tensor product is a very, very subtle notion. It is much more elaborate or much deeper in many ways than direct sum. It is not at all simple to define the direct product concept in a basis independent way. It can be done, but it is quite subtle. I will see if there is time. I will try and describe a basis independent way of defining the tensor product of 2 vector spaces. But let me assume that you know how this is done. Then what is, so I am assuming you know what's the tensor product of 2 vector spaces V1 and V2. Assume always both are complex or both are real. Let's say both are complex. What is the most general vector belonging to this tensor product? Someone tell me. Most general vector in the tensor product space.
V1 tensor V2.
Ah.
V1 belongs to capital V1.
Let us use x's and y's for vectors.
X tensor Y,
Ah.
where X belongs to V1 and Y belongs to V2. No, that's not
I caught you.
And sigma of X tensor Y. Yeah.
The most general element in V, what is it like? He told you the answer, but you tell me.
It is the sum of vectors, linear sum of vectors. Of the
Linear.
form, X tensor Y, where X belongs to V1 and Y belongs to V2.
Right. So you take any number of such things, you can add them, you can multiply each one by a scalar, the result is always in V. And there is no unique way of expanding a vector in V as a sum of these dyadic terms. There is no unique way, many, infinitely many ways. But what you now do is the following. You say, if I take a special kind of vector, I think this notation is not right, I'm sorry, x1 in V1 and x2 in V2. This is not the most general vector, it's a special kind of vector. First you say the definition of the direct product representation is such that on these special product type vectors it acts in a very simple way. That's the first step. Second, you say the most general vector in V is a linear combination of such special vectors. Define D on them by linearity. And I will not even write it, and you can see that D of G is in that way defined on the whole vector space capital V, and it is a group representation. So these are the two important operations: direct sum of two representations, direct product of two representations. So you see, in the direct product case, it is a little more elaborate construction. I don't want to say complicated, I just say elaborate. More ideas have to go into the construction, that is all. Next important concept is the character of the a representation, and this is also something we will keep coming back to quite often. This is defined most simply using the matrices of a representation. So representation D of G on V is given. Choose some basis. Here I am contradicting myself. I am defining something with the help of a basis and then telling you it doesn't matter what basis you choose. The symbol for a character is chi. The character of the representation D is a function of group element, and it is a sum of the diagonal elements of the matrix representing the group element. So it is trace of D of G. So this is the definition of the character of a group representation, and having defined it using a basis and the matrices of the representation, we see immediately that if one were to change the basis, what happens to the matrix? It undergoes a similarity transformation. Trace does not change. So the character of a representation is basis independent. It belongs to the representation alone. It is in general a function on the group which takes complex values. In general, for each G, the character has a complex value at that point. But it has some special property. It is constant over each equivalence class. Why is this true? Why is the character the same at all points of a given equivalence class? Huh? Because yeah, what is the similarity transformation involved? Not change of basis, no. This is trace of D of G prime G, G prime inverse. First you use the group representation property. D of a product of elements is a product of the D's. Then you use D of G inverse is inverse of D of G. So all the properties of a group representation go into convincing yourself that this is a constant over each equivalence class. So I wanted to be clear, it is not coming from invariance under change of basis. It is coming from all the properties of a group representation. Group multiplication law, the inverse of an element, both of them. So it is called a class function. On each class in the group, it has some numerical value, complex numerical value in general, which depends on the representation which you are using. Now we have a 30-second. I leave it as a very trivial exercise for you to show the following. The character of the direct sum is the sum of the characters at each group element. And what about the direct product, character of the direct product? Huh?
Character in D1 into character.
Correct. Characters multiply when you take products of group representations. So these two are things which you should prove or verify for yourself. They are quite obvious. We will see soon that a representation is completely determined apart from equivalence by its character. So this is a very powerful idea, that the character of a representation can completely fix the representation apart from similarity transformations. Of course, I am talking here of finite groups and compact groups only. All right? So it's a very important concept. And we will see all the properties of characters in a little while. So it's quite amazing that to give a group representation, let us say in the matrix picture, is to give a collection of matrices obeying the group composition law under matrix multiplication. Quite remarkable that a numerical function, complex in general, is enough to determine all the matrices up to an overall similarity transformation. That means up to equivalence. That's quite remarkable. These are things which were proved by the pioneers, by like Frobenius and Schur, in the early history of this subject. Okay. Given D of G on V, representation D of group G on vector space V, we say it is reducible if the following is true. If there exists a non-trivial invariant subspace V sub 1 contained in V. What does it mean? So I've written invariant subspace. What does it mean? V1 must be a subspace in V, and it must be non-trivial, which means I don't want to consider V1 equal to 0 or V1 equal to the whole vector space. Those would be the trivial cases. The requirement of invariance means for any group element and any vector in the subspace, action by the representation must leave it in that subspace. Then we say that subspace is invariant. That's a definition of a reducible representation. You are given a representation in a vector space. You may restrict yourself to a subspace, a part of the vector space. There also the representation conditions are satisfied. Naturally, no such V1 means the representation is irreducible. And often the short term irrep is used for irreducible representations. All right. Another acronym, suppose it is unitary and it is irreducible. Everybody writes that as UIR, unitary irreducible representation. Okay. So this is a crucial concept, reducibility and irreducibility. So reducible representation means inside the given representation there is a smaller representation. Suppose now the representation is reducible. One can ask the following question. The invariant subspace V1 is given to you. You ask the question, can we find another subspace V2 in V such that the whole space is the direct sum of V1 and V2, and V2 is also invariant. That is, vectors in V2 are taken by the original representation into vectors in V2.
V minus V1.
Huh?
V minus V1.
What is V minus V1? There is.
We cannot take all vectors in V which are not in V.
That's not a mean. We have not introduced scalar product. And if you say all vectors not in V1, they don't form a vector space. You check. They will not form a vector space. Because the 0 is also not, that's a very simple argument. So it is not V minus V1. So you have to think a little more about it. Does Simon have any illumination to shed on this now? So we ask the question, in the reducible case, somebody has told you, I have found an invariant subspace V1 in the big space V. Then you ask, can you go ahead and see if there's one more invariant subspace V2 with these two properties? V must be the sum of V1 and V2. V2 must also be invariant. If it is possible, if the answer is yes, then we say the representation is decomposable. If the answer is no, we say it is indecomposable. Very soon I will draw a chart for you where all these ideas will become very, very clear, the arrangement of ideas. Yeah. Yeah, and if the representation respects the scalar product. All right, so two conditions. We'll come to that. What you say is correct. If one has a unitary representation, it will always work. But let me go reach there step by step. So here is the arrangement of ideas. Representation D of G on V. This is our starting point. One thing which may happen is that it is an irreducible representation. What does it mean? No non-trivial invariant subspace V1. I omit the word subspace. No non-trivial invariant V1. Reducible, there is a V1 in V It is non-trivial, that means it is neither 0 nor the full space, and it is invariant under the representation. Then you have a reducible representation. Then you say, in the reducible case, it might be a decomposable representation. When is that? It is decomposable if I am able to write V as the V1 plus some other subspace V2 in the form of a direct sum, V2 also invariant under the representation. Indecomposable means no such V2. V1 is there, but you are unable to supplement it with another subspace V2 with this property. So you can appreciate, so this is the flow, the sequence of ideas. Start with the representation. We will see soon conditions which will tell you criteria for irreducibility. We will come to that. That is one of the sure theorems. If a representation is irreducible, very good. It is already a primitive thing, cannot be broken down into anything smaller. If it is reducible, the subspace V1 is there, it is invariant. The group action on V1 gives already a representation smaller than the original one. You can then ask, can I supplement it with another subspace V2 with this direct sum being equal to V, with V2 also an invariant subspace? If so, you can see the original representation has become the direct sum of a representation on V1 and a representation on V2. Just the inverse of what we did earlier today, the direct sum of two representations. Here we are trying to decompose a given representation into smaller pieces. The representation may be reducible, but it may not be decomposable, may be indecomposable. That can also happen. So in matrix language, this can be described in the following way. The reducible case means that in a suitable basis in the whole vector space, all the representation matrices can be brought to this form, where in the southwest corner there is a 0, rectangular matrix 0. On the diagonal, block diagonal, the set of matrices D1 of some dimension describing the representation in V1. Now, if it is possible to reduce B to 0, then decomposable. If this is not possible, it is indecomposable. So you can get a picture of it in matrix language. Okay? So it's that in the indecomposable case, whatever choice you make is indecomposable. Okay. Of course, even in the indecomposable case, always hanging around, the D1 matrices of course give you a group representation. so do the D2 matrices, but D2 carrying that representation. That is what your subtle point. So I think I will stop at this point, just a history point. About 33, 34 years ago, I was a PhD student here at the University of Matthew. His name but I forget his initial. MT. MT Simon. Showing that some properties of photons, some properties in quantum electrodynamics can be traced to the fact that a certain representation of the Lorentz group is indecomposable. I just want to say it is not a rare phenomenon, it's a very interesting thesis, and that is what he had shown. He had drawn out very nice physical consequences of a certain representation being indecomposable. It was related to the masslessness of the photon. So we have. And it was the first, I'm confessing, it was the first time I was asked to evaluate a thesis. I took my work too seriously. I corrected every misprint, every punctuation. And sorry to say, I did not appreciate the work as much as I should have. I did say good things, we passed the student, but I did a lot of unnecessary comments about spelling. Nice thesis, and I have evaluated theses of many of those Matthew students. M. Lakshmanan, Richie, Swami in Nellore Mutt, Prabhakaran, and others also I have evaluated. And I must say, I think Professor Matthews had a lot to do with the writing of those theses. Language was so beautiful, so lucidly presented, the arguments, motivation, it's always a pleasure to read the theses written by Matthews students with his guidance. So this is just to say, it's found a very nice application in this physical context. So I stop it.
Let's go.